All right, so if you guys remember, combustion is always where you have a hydrocarbon like CH4, and it is reacting with oxygen, so O2. And the products of combustion are also always going to be carbon dioxide and water. Okay, so that just keep that in mind. Combustion always means reacts with O2, and you're going to make CO2 and H2O with your hydrocarbon. So if you balance it, you should get a 2 right here and a 2 right here. All right, so for the first part of the question, it's asking about the disappearance of CH4 in relation to CO2 production. So we just look at the mole ratio. If you look, how many moles of CH4 do we have? 1. So it'll be 1 mole of CH4, and how many moles of CO2 are being produced? 1. So it'll be 1 mole to 1 mole, and so you can say for this one right here, it is equal. Okay, you can say it's equal, you can say it's 1 to 1, something along those lines that communicates the same thing. All right. Now for H2O, it's a little bit different because the coefficients are different, right? So we still got 1 mole of CH4, but what do we have? What's the coefficient for H2O? 2. So it'll be 2 moles of H2O. So the rate of disappearance in relation to H2O production will be 1/2. Okay. So if we wanted to be a bit more detailed with the way that we wrote that, we would say that the rate of disappearance of CH4 is 1/2 H2O production. Okay, so the rate of disappearance of methane is 1/2 H2O production. And I believe I mentioned it while we were doing the lectures, but if we worded it differently, let's say, for example, the question was asking, what is the rate of production of H2O in relation to CH4? Then we say the rate of production of H2O is times 2 CH4 disappearance. So whatever it is asking you to compare, the order matters. If it asks for in relation, the way that it asks in relation, it's going to flip your fraction up and down. Okay, so just be careful of that. I did mention it during the lecture, but a question like this will be on your test. Okay, so just make sure you're very careful and you know how to set up this fraction properly to get the correct relationship. Yeah.
So if you were to switch what it has as the rate of production of H2O.
Exactly like that, yes, yeah. It'll be rate of production of H2O in relation to disappearance of CH4, yeah. Yeah, it's just wording, semantics, pretty annoying, but it does, yeah, it does matter. Okay, let's go to number 2. Let's talk about a catalyst. If you remember, a catalyst is a compound that supports or that increases the rate of a reaction. But let's talk about how it affects a reaction coordinate. So if you remember, you have a reaction coordinate, and this is going to be the energy in the system, and then this is going to be the progress of the reaction. We know that every time there's a reaction, there is an activation energy barrier it needs to overcome. So anyone remember, how does a catalyst affect the reaction coordinate?
It decreases.
Yeah, it decreases what?
The amount of energy required.
Yeah, what's that called?
Activation.
Activation energy. So keep that in mind. It decreases the activation energy, but it does not change the delta H. Okay, so it does not affect the relationship between the reactants and the products. That's this arrow right here, the black one. But it does affect this arrow right here, the blue one, the height of the activation energy. Okay, so it lowers the energy required to start the reaction, but it does not change the actual change in energy of the system. Okay. All right, any questions on that right there? Again, that will also be on your exam, so keep that in mind. AP Test loves to throw this in there as well. All right, so let me give you guys about 2 minutes, and I want you to draw the reaction coordinate for number 3 of an endothermic reaction. Endothermic reaction. Take about 2 minutes to do that, and then we'll go over that before moving on. So for an endothermic reaction, same thing. It's a reaction coordinate. So we got energy on the y-axis. We have the reaction progress on the x-axis. And if you remember, if it's endothermic, what has a higher energy, the reactants or the products? The products, yeah, because absorbing energy. So what you would do is you would just very easily just set a line for your reactants, and it has to be under your products. And again, there's an activation energy barrier, so it needs to go up, and it needs the peak of that barrier needs to be higher than your products. Just keep that in mind. So you got your bump, and then products. That's endothermic. Easy peasy. So again, just to call back to number 2. For number 2, the catalyst will reduce this activation energy barrier right here. It'll just make it shorter. All right, so for your rate law, it's just K, the constant, times the concentration of your reactant. So you got ClO2 and F2. And we got to look at the experimental data. So we're going to keep ClO2 constant right here. If you keep this constant, let's look at how F2 changes. So we are doubling F2, and if you double F2, what happens to the, yeah, you quadruple, thank you. So if that happens, what is the order of F2? Second order. Good.
Why are you sticking your tongue out?
Everybody good? Okay, because you double it, and then you get exponential growth, so you get times 4 there. So that's second order. All right, let's go to ClO2. For this one, we're going to hold F2 constant. And if we double ClO2, what happens to the rate? It remains the same. So what type of reaction order is that?
Zero order.
This is 0 order. So if you are simplifying the rate law, it will just be rate is equal to K. Anything to the power of 0 is 1, so we can omit it from our equation. So it'll just be KF2 squared. That's it. Any questions on the rate law? Okay, so to find the rate constant is very simple. We just need to plug in our value. So I'm just going to pick a random trial. Let's just pick 1 just because it's the first one. So we're going to plug in our values. The rate is going to be 2.4 times 10 to the negative 3, which is the same thing as 0.0024. And it is molarity per second, is equal to K. And then our concentration of F2 is 0.1. So 0.1, but concentration is molarity squared. Now, we don't care about ClO2 because it is 0 order. It does not affect the rate at all. Let me give you about a minute and a half. See if you could solve for K. And again, make sure you get the correct units of measurement. So try that out. All right, everybody. So your answer should be 0.24 per molarity per second. And the reason why I have the work up there for you, you have the numbers filled in. You have to square 0.1, but you also square the molarity. So you get 0.01 molarity squared. And you just isolate the K by dividing. That'll give you 0.24 for your numbers. The molarity on top of the fraction cancels out with 1 of the molarities. And so that's on the bottom of a fraction, so you'll end up with molarity negative 1. Seconds already on the bottom of a fraction, so seconds negative 1. So that's your units of measurement. All right, so number 5 is a half-life problem, and it gives you some information about it. So it says that you got a radioactive isotope that produces 4,000 counts per minute on a Geiger counter. And after 120 hours, the sample produces 125 per minute. So what it tells us is that we start with 4,000 counts, and then it ends up at 125 counts, and that total amount of time is 120 hours. Okay, so we want to calculate the half-life of an isotope. And remember, every time that it decreases in half, that is 1 half-life. So we just need to figure out what the halves are. So let's start with 4,000. What is half of 4,000? Yeah, 2,000. So I'll put it right here. 2,000. And then what is half of 2,000? 1,000. Half of that? Yeah, 500. And then 250. And then lastly, we get to 125. So I like to do it a little bit like this number chart because you can visually see how many half-lives there are. So there is 1, 2, 3, 4, and 5. There are 5 half-lives. So 5 half-lives is equal to 120 hours. So the math is really easy. You just need to divide by 5. Okay. And that will give you 24. So 1 half-life is 24 hours. That's it. That's half-life. You will have a half-life question on your test. Pretty similar to that. Keep that in mind. Yeah.
I'm liking this.
Like, what are you talking about?
The heck? Stop talking about my family. You're so weird. You don't even know my family.
The little sister calls me all the days. I'm trying to lock in on AP Chem. Look, I think it's one of the oldest.
Did I ask? I want to see
Yeah, so you're not getting
who got a higher score on the last test? You remember?
Biker.
Oh wait, not highest.
Highest?
Biker. You're my saving grace.
Who got the highest?
Mike is not even going to take the test.
I haven't taken it yet.
Like, it's gonna be my saving grace. I'm not counting out.
You know, I'm giving you a different
Mike
test than the
gets a
other two,
higher
right?
score than me. That doesn't
It
matter.
wouldn't matter. I haven't.
What? We can go? I'm just not going to eat it and say we can't get it. Oh, yeah. I thought like they did not have kids. I was like, they did not get
Started recording. Started recording.
Yeah, I know. I'm typing. Thank you, though.
Hi, fans.
Like,
He's not gonna edit it. He's so lazy.
I just have better things to do with my time than just. Okay, so for this one, we have step 2 as our slow step. So similar to what we've been looking at. So we're going to write the rate law for step 2 first. So the rate is equal to K, and I'm going to just say K2. Concentration of NO3, NO2. All right. Everybody good with that? That part's pretty easy, right? Now, what is the issue with this rate law? Yeah, what's the intermediate? What was it? NO3. Yeah, just NO3. And that's why this is a little bit different. Because if you look, NO2 is a what? Product. Yeah, we make it so this can be part of the rate law. But NO3 cannot. So NO3 is the one that we need to replace. So we're going to look at the previous step before, the equilibrium step, to do what we did with steady step. So the rate forward is equal to the rate reverse. And we are going to expand this equation out. So the equilibrium constant for the forward reaction is N2O5 equals K reverse is NO2 NO3. All right, everybody good so far? Okay, now, what variable are we trying to isolate for? NO3. Yeah, we want to isolate for NO3, so we got to move everything to the other side. So that is going to give us KF divided by KR. And then we're also going to get, we got to keep the N2O5. And we're dividing also by NO2 to get NO3. Everybody good? Okay, And then from there, it's just our substitution. We plug this into this equation right here. So if we expanded it out, we will get rate. And I'm just going to get rid of the K's right now, if that's okay with you, just to save some space. We'll get K overall. And by writing K overall, we will get rid of K2, KF, KR. And then we substituted NO3, so we would get NO2. And then we got a fraction right here, times N2O5, NO2. All right, but if we do that, what happens to the NO2s? They cancel out. And then you will end up with the rate being equal to K overall.
Great. So
Yeah, and it looks like the same thing that we did, but these steps are different because if we didn't have that, then it would come out a different answer because we wouldn't have to cancel out.
can you give us an example where it doesn't?
So again, this is from the 2019 AP exam, and it tells us that nitrogen dioxide is produced as a byproduct from the combustion of fossil fuels in ICEs. At elevated temperatures, NO2 is monitored and it decomposes right here. So first you have some information about the background, right? In internal combustion engines, NO2 is created, and it tells you that it decomposes when it's really heated into these two products. And then it tells us the concentration of NO2 is monitored as it decomposes and recorded on the graph. So these graphs are basically telling us the concentration of NO2 over time. And if you look right here, it is an exponential decay. You guys see over time it goes down. Now, question part A is asking us, how does this indicate that the reaction is second order? And then it gives you these three graphs right here. Now, before we do that, I'm going to zoom out a little bit. Again, if you have it on your screen, it's probably a little bit easier to look at. But if you look at it, these are three different graphs. And if you look, the x-axis is the same. It's over time. But if you look at the y-axis, it has different values, right? This first one is concentration. This second one is 1 over the concentration. And this third one is the natural log of the concentration. So do you guys notice how the y-axes are different, right? All right. Now, we didn't talk about this during the lecture because it's not super important, in my opinion, but it does come up now and then like this. And let's talk about let's talk about what these graphs mean. So I'm going to go back to the class workbook, and you'll see this, this table on page 14. And you remember this chart that I showed you guys, right? How different order reactions have different things, right? The rate laws are a little different. The units are different. The half-life formula is different, so on and so forth. Now, there is one component of these reaction orders that we didn't talk about, and it's called a straight line plot, okay? And basically what that means is that at different reaction orders, you can get a straight line for your graph if you change the measurement for your y-axis. So if you look right here for a zero order, when you plot concentration versus time, that's how you get a straight line. For a first order, if you plot natural log over time, you will get a straight line. And then 1 over concentration, you get a straight line for second order. Okay, that's what that means. Honestly, you don't need to memorize this. It's just there for you. If you want a straight line, that's how you plot the two things. Now, for the actual review, that's not that important because we're just going to talk about why it's why we could say a second order. Because we can just use the one that we're most comfortable with, the concentration over time. And if you look, what do you notice about the decay? Exponential. So you can just say it's exponential. So you know that it is second order because it decays. It has an exponential decay. Okay. Another one that you could have said if you look back at the chart, if you plot 1 over the concentration versus time. That's how you get a straight line. You could also write that. Honestly, you can even deduce that because you see a straight line, it tells you the second order, and you can just say, even if you didn't know, you can say, oh, when you plot 1 over concentration versus time, you get a straight line. So even without memorizing it, you could have just talked about both reasons. But I think the easiest way is the exponential decay. Okay, either will work. Okay, guys, so if we take a look at this problem, it tells us the order of the reaction, right? What's the order? Yeah, it tells us that it's second order, right, in the previous part. And if you look at the reaction, the only reactant is NO2, right? So the rate is equal to K, concentration of NO2, second order, so squared. That's it. That is the answer for part B. If we take a look at part C, there are 2 parts to part C. And basically, they give you different mechanisms, and they ask, is this consistent with the rate law you wrote in part B? So, just a reminder that the rate law that we wrote was the rate is equal to K, and then the concentration of NO2 squared, because it's second order. So if we take a look at part 1 here, you get the mechanism. It's a multi-step, and it tells you that this is the slow step. So we're going to look at the rate law for the slow step. The rate law for the slow step is the rate is K, and then there are 2 separate molecules of NO2. So we're going to write that down. Now, if we simplify this, what does the rate law, what do the NO2s turn into?
NO2
Squared. So it'll be NO2 squared. So does this match with the rate law we proposed? Yes. So your answer would be yes. And then this would be your justification. You would explain that you use the slow step as your rate law. There are 2 NO2s, and if you multiply, that becomes squared, which is the exponent you want for the rate law. All right, everybody good? You would want to show your work and then just write a brief blurb explaining it. Yeah, probably something about the slow step defining the rate law, which turned into this. Yeah, great question. Yeah, when there's justify, usually you want a calculation and explanation. Okay, let's go to 2. 2 is different. It's a different mechanism, and the problem is this is a slow step. But what's N2O4? It's intermediate, right? So this cannot be part of the rate law. So we would have to do steady state in order to write the rate law. Because again, we cannot have N2O4 as part of the overall rate law. So let me give you about 2-3 minutes to do that. See if you can get the rate law, and then you're gonna write, is it consistent with the rate law that you proposed? So try that out. Do the steady step. All right, guys, we got the answer up there, and the answer is yes. Okay, we do steady step. You get the same rate law. So if you actually look at this, we don't know what the mechanism is because it could be either or. Who knows?